Every year, GE hosts a computer science competition with UConn. The competition is split between an individual written test and a team case study. In the past, our members have done pretty well on the individual test, but we wanted to try to do well on the case study as well.
This is the dungeon maze. The case study was simple. Write a program to get to the end of a maze.
The case study this year was a maze where we have to find the exit, which we don't know where it is. So there are a lot of challenges to find it, and one of them is vision. We are given a vision radius by the GE team, and it's different every time, and we can figure out what it is, but that is a challenge because if they give us a vision radius of 5, it means we can only see 5 blocks up, 5 blocks down, 5 blocks to the right, and 5 blocks to the left. So if we're looking down a hallway, we might not be able to see the entire thing. It is blocked by walls and doors, so we have a very limited vision. Another challenge is that the keys and doors, we also don't know where they are. We don't know where anything is on the map before we go into it. So we need to discover keys and discover doors, and we're not really sure if those will lead to an exit, but picking up keys allows us to go through doors which may or may not lead to an exit. Here is a picture of the map. As you can see, we're this greenish yellow square, and basically our vision here is going down, and one block after to the left and right down the hallway we can see just around the corners, and also up we can see these two and the one to the left. We cannot see this door or this space in this hallway or this exit right here, but we go down. Our decision making will make us go down this way because we have already come from this way. So we go down this way and we see this door, and then we don't have a key, so we go down to the left, and you can't see it on this image, but there's a key down here, and then we go through the door and get to the exit.
The map contains various elements. One of the most important elements is us, here, the player. The player will change color between green, yellow, and blue. In this stage, it's yellow. Another important element are the keys. Here, here, and here. The keys are needed to unlock the doors. The doors are here, here, and here. And they're treated like impassable terrain until we open them with a key. Finally, we also have the exit here. The game ends when we step on the exit. We don't need to do anything special, but that is the ultimate destination. What was the first thing you thought of when you saw the task?
I thought it was going to be really based on luck and like random number generation, because we were not really given much vision of the map, and we really didn't know anything about the challenge before going into it.
The first thing I thought of when I heard of the challenge was we were probably going to have to use some type of statistical inference or some sort of statistical method.
What did the GE computer science team look into before pursuing the actual implementation?
One thing that we looked into before we pursued, before going forward with the solution we went with, was SLAM, or simultaneous localization and mapping. But that's a process where a robot takes like landmarks and distances to landmarks and uses that to try to find out where it is in an area. But we did end up using most of what we learned because that has to deal more with physical objects.
We looked at a statistical inference that was used, the way it was used in the PDF was farmland, and how to infer what a type of land is going to be based on what you've seen of other lands. Likewise, in our challenge, we were going to do it so that we could infer by seeing a certain percentage of open or closed blocks whether or not the next block that we discovered is going to be open or closed.
What was the final method agreed upon by the team?
We ended up going with a priority list system in conjunction with Dexter's algorithm. The priority list system basically said, if we can see an exit, go to the exit. If we can see a key, go to the key, etc. And down to like the most simple form of going down to an open block. And once we knew where we needed to go, we used Dexter's algorithm to find the shortest path to that point.
This is an example of Dexter's algorithm, which is what we used to pathfind in our case study. Basically, it branches out, and every path that it takes, it keeps going in all directions. And when it hits an edge, like it does here, it throws out that path and doesn't even consider it in order for optimization. And it keeps going, branching out in all directions until it actually finds the point where you're going. And once it does that, it analyzes all the paths that it's found up to that point and takes the shortest one by just checking every single path until it gets to the shortest one.
What was the full list of priorities that you guys had come up with?
Well, the first priority we had, of course, was to go to the closest exit. The reason we say closest is because we weren't sure if there was going to be more than one exit. I believe on one of the test maps there was 2 possible exits. The next priority was a key, because we wanted to be able to explore as much of the map as possible. So we would need keys to open doors to do that. Then if we had a key, you would want to go to a door, which to the nearest door, because there could be more than one door. And if we didn't have a key, then we would go to the closest unexplored area, unless there was an unexplored area behind us that was closer. Then we would backtrack to that new unexplored area.